So in this video, what I want to do is to consider the curl of the curl. So we have a vector field that I'm choosing to call A, and we take its curl, that gives us a vector field, and then we take the curl again, and we will obtain overall a vector field. And I want to obtain an expression for it. The notation that we're going to use is that our vector field A has component A1 in the I direction, component A2 in the J direction, and a component A3 in the K direction. And the result that we're going to obtain is that the curl of the curl is equal to the gradient of the divergence minus the Laplacian acting on the vector field. So let's just think about what this means before we get stuck into the calculations. So A is a vector field. We take its divergence, and that gives us a scalar result. But when we take the gradient of that, we obtain overall a vector. So this vector is equal to a vector field minus this. Now A is a vector, and we are here applying the Laplacian to it. So the Laplacian of a vector field means the Laplacian acting on A1 in the I direction plus the Laplacian acting on A2 times J plus the Laplacian acting on A3 times K. And just to be very concrete, if we're thinking about here, the Laplacian acting on A1 is d2 by dx squared of A1 plus d2 by dy squared of A1 plus d2 by dz squared of A1. So all of those three terms multiplied by I, and similarly for here and here. So to calculate this, we're going to need, of course, to know our formula for the curl, and I've written this formula out here. So we can obtain it just by expanding across the top row, and what we are going to get if we do that is, so in the I direction, we forget this row and this column, and we differentiate A3 with respect to y, and then we subtract, and now we differentiate A2 with respect to z. So what we obtain is dA3 dy minus dA2 dz, close brackets. We then go along the top row, we put in a minus sign, and in the j direction we now expand, ignoring this row and this column, and what we obtain is dA3 dx minus dA1 dz. And then we add, and now in the k direction we ignore this row and this column, and we have the derivative of A2 with respect to x minus the derivative of A1 with respect to y. So we have dA2 dx minus dA1 dy, close brackets. And this result here is basically fine, but we have this extra minus sign here, so let's just rewrite it and get rid of that minus sign. So I'm going to multiply here by a minus sign and here by a minus sign. And if I do that, what we're going to get is that the curl of A is equal to I dA3 dy, not changing anything here, just rewriting it out again, dA2 dz, and now it's plus j, and now I write the other term first to stop leading with a minus sign. So I'm going to write dA1 dz minus dA3 dx, close brackets, plus k, and here I just write out again what we have on the line above. So we have minus here at the end, dA1 dy, close brackets. So now we have an expression for the curl of A, and we want to take the curl of this result. and I'm going to write that out on the next page. So on the previous slide, we calculated the curl of a vector field that we called A, and we found that this was the formula. And what we want to do now is to calculate the curl of the curl of A. And we could start from scratch again and just use this as the bottom row. But another, I think, quite elegant way to do it is to say, well, this is actually the curl of B, where we say that B is this vector field, and B has components. This is B1, this is B2, and this is B3. So all we have to do to write down the curl of the curl is to reuse this formula, but everywhere where there is an A, replace it by the relevant B. So what we're going to obtain is that this is equal to, in the I direction, it's d by dy acting upon, and now instead of A3 we write B3, so that's this combination expressed in terms of A's. So it is d by dy acting upon dA2 dx minus dA1 dy minus, and now it's d by dz, and instead of writing A2 we write B2, and B2 we know is this, so it is dA1 dz minus dA3 dx, close brackets, close the big brackets at the end. So now we've written out the I component, and the j component is going to be plus j, and again we're just using this formula here, but everywhere we're replacing A by the relevant B. So it's d by dz of A1, so d by dz of B1, and this is B1. So what we obtain is d by dz of, and B1 is dA3 dy minus dA2 dz minus, and then the next term is d by dx here, acting upon, now it would be B3, and this is B3, so we just write it down, dA2 dx minus dA1 dy, close brackets, and then in the k direction it's plus k, open brackets, and it's d by dx. Previously it was A2, we replace that with B2, which is written here, so that's open brackets dA1 dz minus dA3 dx, close brackets, minus d by dy, which we see from here, acting upon what would now be B1. This is B1, so it's dA3 dy minus dA2 dz. So I think that's quite elegant, and if you're not sure that you completely believe it, you can just write out the curl again of this expression and use for the bottom row in the determinant this set of coefficients. And this is what you will obtain. So now what we have to do is to calculate these derivatives, and you can see that we're going to have mixed derivatives, and we're also going to have second derivatives, such as this term here, which is the second derivative of A1 with respect to y. So we're just going to expand that out and see what we get. So I'll put my equal sign a little bit more to the left here to give myself a little bit more room, and we have I. So it's d2a2 dy dx minus d2a1 dy squared minus, now carrying on expanding this, and it's d2a1, it's the same thing, and now differentiated twice with respect to z, and then we get a plus sign because it's minus minus, and it's d2a3 dz dx, close brackets. And that looks quite nice, but let's just write out the other terms and we'll come back to it. So we have plus j from the second row, and that's d2a3 dz dy minus, and now it's a second derivative, d2a2 dz squared minus d2a2 dx squared coming from here, and then minus minus is going to give us plus, and it will be this second derivative of a1, so it's plus d2a1 dx dy, close brackets. And similarly from the final terms in the k direction, it's d2a1 dz dx dz minus d2a3 dx squared minus d2a3 dy squared, and then finally plus, because of the minus minus combination, d2a2 dy dz, close brackets. So let's pause a second and look at what we have here. And the first thing that I would notice is that these two terms look like part of the Laplacian acting on a1. These two terms look like part of the Laplacian acting on a2, and here we have part of the Laplacian acting on a3. In each case, one of the terms is missing. So let's look at this top row here. If we had minus d2a1 dx squared as well, we would have the Laplacian acting upon a1. So what I propose to do is, inside the brackets, let us add and subtract in the brackets d2a1 dx squared. And similarly in here, we are going to add and subtract d2a2, and the term that's missing here, if you look at it, is d2a2 dy squared. And finally here, we are going to add and subtract d2a3, and the term that's missing is d2a3 dz squared. So if we do that, what we're going to have in this brackets is this term and this term, and the term that we are adding, and the three terms that we're subtracting, this one, and when we subtract this, are going to give us minus the Laplacian acting on a1. And similarly here, there will be three terms with plus signs, these two plus one more, minus the Laplacian acting on a2, and similarly down here. So what I want to do is just pause and try and make this a bit smaller so I can try to fit everything in on this one screen. So as discussed, what we are going to get is in the I direction. So I'm going to first write down the term that I'm adding here. So I'm going to write down d2a1 dx squared, and then we've got plus d2a2 dy dx coming from here, And then we've got this term, which is also positive, so I'm going to write it next. And that is plus d2a3 dz dx. And the three terms that are left, as we have said, are just minus the Laplacian acting upon a1. So remember, the Laplacian acting on a1 is d2 by dx squared on a1 plus d2 by dy squared on a1 and d2 by dz squared acting on a1. And we're now going to have all of those three terms, this one, and when we subtract this one, all with minus signs in front of them. So that's what we get from the top row with this addition and subtraction. Similarly, what we're going to get for the second row, so the terms in the j direction, is going to be, so it's d2a2 dy squared. That's the term we have added and subtracted, but I'm just writing down the one we're adding, plus d2a3 dz dy, plus, let's write down the other positive term from the end of the brackets here. So that's d2a1 dx dy. And the three terms that are left are minus the Laplacian, all acting upon a2. So it's minus the Laplacian of a2. And then the third term, I'll try to fit it in here. In the k direction, we're going to get three positive terms, this, and this, which I will write down first. So that's d2a3 dz squared plus d2a1 dx dz. That was this term, plus this term, so that's plus d2a2 dy dz minus the Laplacian acting upon a3. Close brackets. So that's an a with a 3 subscript here. You can see the a3 here, here, and here. So this is our result, and these three terms look very nice, and in a moment we're going to rewrite them because they're all minus the Laplacian, and it's acting upon a1 plus j_a2 plus k_a3. So these three terms with the i's, j's and k's correspond to minus the Laplacian acting on the whole of the vector A. So ia1 plus ia2 plus ia3. So what we have to do is to try to simplify these terms and see what we can get out of that. So let's look at this. I'll change the colour. So in the I direction, and I'm now just going to look at the positive terms because the terms that we're subtracting, we've seen how to rewrite them. I'll just write them at the end. So here, these positive terms, they have all got a derivative with respect to x. So every single one has at least one derivative with respect to x. So I'm going to write I d by dx acting upon, and then let's see what is left inside here. Well, we'd have 1 d by dx of a1, and we'd have plus d by dy of a2. Once we've taken out the dx derivative, we're using equality of mixed partials that we can swap the ordering around. And then here again, we pulled out the d by dx, and we're left with d by dz of a3. So that is, I'll just write it out very explicitly, it's dA1 dx plus dA2 2 dy plus dA3 dz. Oh, that we recognize, I hope. That is the divergence of A. So this is I d by dx acting upon the divergence of A. Now if we look at this and this, what we will see is that we get plus j, and we've got in every term here, we have got at least one derivative with respect to y, so I can pull that outside, and it will again be seen very quickly to be acting upon the divergence of A, because here, once you'd pulled out the derivative with respect to y, you would be left with dA1 dx plus dA2 dy plus dA3 dz. So again, that's this term. And then similarly from the final term, we will have plus k. The derivative that we pull out is with respect to z, and the three terms come together to give the divergence of A. And then, as previously noted, all the terms we're subtracting correspond to minus the Laplacian acting upon the vector A. So that's I A1, J A2, and K A3. This term has the same form as this, and what we see is that we have I d by dx acting on a scalar, this divergence, plus j d by dy acting on the scalar, the divergence, and k d by dz acting on the scalar. That is therefore equivalent to the gradient of this scalar. So I'll just pause and make some space. So I've made a bit of room and I can write down our final result, and the result we've seen is that the curl of a vector field I'm calling A is equal to the gradient of the divergence of A. That corresponds to these three terms here. So it's I d by dx on the divergence plus j d by dy on the divergence plus k d by dz on the divergence. That's what we have here, minus the Laplacian acting upon the vector field A. And that is the result that we wanted to show. So as required. So just to go over this side again, and I think it's worth doing on a piece of paper, be actively involved with it rather than just watching it. What did we do? We calculated the curl on the previous side of a vector field, and then you can either take the curl of this again just by using the same method, or what I said was to take the curl of a curl, we just take the curl of B, where B has the components of the curl of A. So that's B1, B2, and B3. Either way, you will obtain that the curl of the curl has this form here. We expand things out, and what we noted, the thing that gave us the idea that we needed, was that these two terms here were 2/3 of the Laplacian operator acting on A1. So we said, let's subtract the term we need to have the Laplacian acting on A1, but also add the term we need so that we're not changing anything inside the brackets. And we did essentially the same thing here and here. It's just the terms that we add and subtract are different in each of these sets of brackets. I then wrote down the positive terms in each case, and subtracted the Laplacian acting on A1, A2, and A3. And then in each of these terms, these are second derivatives, but here there is always a derivative with respect to x. So I said, let's pull it outside. Here there is always in the j direction, derivative with respect to y. So I said, let's pull that out. It's here and here and here. And in the k direction, there is always a derivative with respect to z. So we can pull that out. And what we see when we do that is that we are left with the divergence. So this derivative with respect to x is acting upon the divergence of A. And the same thing is happening here. These terms, 1, 2, 3, correspond to the derivative with respect to y of the divergence of A. These three are the derivative with respect to z of the divergence of A. So we have the gradient of the divergence of A minus, and apologies, I'd forgotten to put the 2 there, the Laplacian acting on the vector field A. And with that, I will stop this video.